Welcome to another day on the Journey Chez Chem. Please do the 2 warm-up questions to the best of your ability, and we'll go over them in a moment. The question in number 1 is asking us to change from formula units of sodium carbonate to mass in grams. I begin with my original number over 1. Then I change my formula units to moles. I always go to mole central. And 1 mole of sodium chromate is Avogadro's number of formula units. Formula units are tiniest of particles. Therefore, I need many, many, many of them to get to a mole. Now, once I go to moles, I can go to mass. And in order to do that, 1 mole must be in the bottom, and the AMU in grams must be on the top. Now, we have 2 sodiums, which is 2 times 23.0, and we have carbon, which is 12.0, and we have 3 oxygens, which is 3 times 16.0. I get 46.0, 12.0, and 48.0, which when I add those numbers up, I get 106.0 grams per mole. Therefore, 1 mole is 106.0 grams of sodium carbonate. In my calculator, when I do this math, I'm going to take my original number and divide by 6.02 times 10 to the 23rd, exponent 23rd, not times 10, equals, and then times 106. And the answer that I'm going to get is 24.1229. We take numbers 4 places after the decimal and cut it off or truncate. Then I look back at my original number and I have 3 significant digits. Therefore, I want 3 significant digits in my answer. And my answer will be 24.1 grams of sodium carbonate. That is my answer to number 1. In number 2, I'm beginning with grams of sodium peroxide. Now, this one has an extra step. I begin with my grams of sodium peroxide, and I change my grams to moles. And 1 mole of sodium peroxide, well, I have 2 sodiums, which is 2 times 23.0 from the periodic chart, and 2 oxygens, which is 2 times 16.0, and I multiply them out, and I get 78.0 grams per mole. Therefore, that number will go in the bottom. Now, once I get to mole central, I can go to my formula units. And there are 6.02 times 10 to the 23rd formula units of sodium peroxide in 1 mole of sodium peroxide. Now, this has 1 extra step because it's asking for the atoms of oxygen. And I have a compound here, so I had to go to formula units first. Then I look in the formula and I see there are 2 atoms of oxygen for every one of these formulas. Therefore, my new conversion is 2 atoms of oxygen in 1 formula unit of sodium peroxide. And when I multiply all of this out, I am going to get 2.1147 times 10 to the 22nd. Then I look back at my original number and I have 3 significant digits. Therefore, my answer should have 3 significant digits. And those are atoms of oxygen. And that is my final answer. Now, in the first one, I could have written it in scientific notation. That would be the same number. It doesn't matter which form. Both are correct. That's number 1 and 2. Now, today we're going to be discussing empirical and molecular formulas, and I'll be back in a moment. Empirical means the simplest, the foundational formula. And I have a simple formula here of CH2O. Now, that is the empirical formula for a compound. And in order to determine the molecular formula, I have to be given the molecular mass. And the molecular mass for this particular compound is 180. In order to find the molecular formula, I must add up the AMUs for the empirical formula. I have carbon is equal to 12. There are 2 hydrogens, that is 2 times 1.0, and we have oxygen, and oxygen is 16.0. I add those up to get the empirical mass, and that would be 30.0 grams per mole. Now, I want to know what the molecular formula is. This is the simplest ratio of the atoms. I divide my molecular mass by my empirical mass, and I see that it goes 6 times. Therefore, I take this formula and I multiply it through by 6, C6H12O6. And you recognize that. That's glucose, and we've seen that before. Now, I cannot write the 6 in front because that would say that that molecule only contains 1 carbon, and glucose contains 6 carbons. This is how it occurs in nature, and this is the simplest ratio of those atoms. This is a concept that we will need to be able to use in what we are determining today. Now, you need to take out the worksheet C, and we're going to go over the example problem together. We are given a percentage, so what we're going to do is assume that we have 100 grams, just like we have 100%. So every percent is equal to 1 gram. And I've given 46.56 grams of iron. And I need to change my grams to moles. I don't like that G, so I'm going to fix it. And when I look on the periodic chart, I see that 1 mole of iron has a mass of 55.9 grams of iron. And when I do the math, I get 8.8329 moles of iron. Now, I'm trying to find a formula for these 2 elements joined together, iron and sulfur. And when I subtract this percentage from 100, I get the remainder. And therefore, the remainder is 53.44 grams of sulfur in this formula. Again, in order to make comparisons, I have to change things to moles. And 1 mole of sulfur on the periodic chart tells me its mass is 32.1 grams. And when I do the math here, I get 1.6647 moles of sulfur. Now, in order to get the ratio, what I need is a ratio of the elements to one another. And I'm always going to divide by the smallest number of moles. It doesn't matter. In this case, I have 2 atoms, but I could have 3 atoms or even 4 atoms, and I want to know their relationship to each other. And I also know that moles must be in whole numbers in the formula because we can't have half of an atom. So I'm going to divide by the smallest number, and obviously this is 1. When I divide this, I get by the smallest number of moles, I'm going to get 1.99. Now, as long as it's within a tenth of a whole number, I can use that. It's fine to round that. But anything greater than that, we would have to multiply by something to get it to a whole number. In this case, we have iron is 1 and sulfur is 2. Therefore, my formula is FeS2. In the formula, there is 1 iron to every 2 sulfurs. Now, the assignment that you have today can begin very simply. If this was a 1-to-1, it would just be FeS. That's a possibility. And you always have to divide by the smallest number of moles in order to get those formulas. Now, the second thing we need to talk about is percent composition. And I don't think you'll have much problem with this. It's pretty straightforward. If I'm interested in finding out about a building that has a bunch of broken windows, and I need to know what percentage of broken windows, I have to take the number of broken windows and divide it by the total number of windows. Very much the same when I want percent composition. Let's say, for example, we have sodium carbonate that we used before in the warm-up. And I want to know what is the percentage of oxygen, the percent composition of this compound of oxygen. I take the mass of 3 oxygens, which would be 3 times 16, which would give me 48.0 AMU. Then I need the total mass of the sodium carbonate, and we did that before, and we found that it was 106. I take my amount of the element I'm looking for in the AMUs, divided by the total mass of the compound, the gram formula mass, times 100, and I get a percentage. In this case, I get 45.2830, and for percentages, just like AMUs, we're going to take that to the tenths place. Therefore, I look at this, and I see that I'm going to round up, and my final answer is 45.3% oxygen. And then I also want to let you know that when we're finding these ratios in empirical formulas, well, when I'm talking about water and I wanted to get the ratio, there's not 2 oxygens in water, there's only 1. Therefore, when I combine atoms together, we're not talking about diatomic molecules anymore. That would be if oxygen was standing alone. But when it's in a compound, it's not diatomic. Just like here in sodium carbonate, we had 3 oxygens, not 1 and not 2. We had to determine that there are 3 in that formula. Well, I hope that helps, and you give it a shot today on the empirical and molecular formulas, and percent composition is what you need to do for the remainder of the time that you have today, and finish it up this evening, and we'll talk about some more tomorrow. Well, it's been fun, and I can't wait to see you. Bye.